This lesson represents a few what I would call wrap-up topics for the course. So the first page talks about something you know very well, the first derivative test. So we use this to figure out if a function is increasing or decreasing, as well as relative extrema, so local minimums and maximums. So I asked you to take this function and use the first derivative test to identify any relative extrema. I took my first derivative, set it equal to 0, did a little bit of factoring, and found my critical points. I then plugged in the first derivative test. So all you're doing is taking values to the left and right and literally putting them into your first derivative and acknowledging their sign. If it changes from negative to positive, you have a relative min. Changes from positive to negative, relative max, and no change signifies no extrema. We know that will definitely be on the test at some point. Something else that will be on the test is the second derivative test. Traditionally, we only use this to find concavity, but you can also use it for relative extrema. So that's what this highlights. You would still find your critical points with the first derivative. That's what I did here. Rewrote the work from above. But instead of plugging them into a number line and using your first derivative, you plug those values directly into your second derivative. So what you're looking for here is simply positives, which signify concave up, and negatives, concave down. Zeros and does not exist won't be conclusive in terms of relative extrema, and that's absolutely fine. So what happened when I plugged in -1 is I got 30. I don't care so much about the value of 30, I care about its sign. Because it's positive, it means your function is concave up. Do a little picture there. Therefore, there has to be a relative min at this value. When I plugged in 0, it was 0, no concavity, no relative extrema there. And 1, I had a negative value, therefore concave down signifies a relative max. So if you were to only know a couple of features, you could be pretty conclusive. So what I mean by that is, for this next problem, you know that it has a critical value. The function is at 6. That means the first derivative at 6 is 0. And they also tell you the value of the second derivative at 6. So once you have that critical value, you know it flattens off there. And once you have this positive second derivative, it not only flattens off, but it's concave up. Therefore, by the second derivative test, you know that you have a relative minimum. Totally switching directions with number 4 and the subsequent problems, we are going to go back to a little bit of differentiation. So this says implicitly take the derivative. If it didn't say that, you would definitely want to use this method because the x's and the y's, the inputs and outputs, are mixed up on the same side of the equation. Most likely on the CCC final, they'll say differentiate implicitly. So I went ahead, I used my product rule here. So it doesn't matter which order you do. I chose to do the voodoo plus udiv. So I kept this as square root of y. Derivative of x in terms of x is dx over dx, plus kept my u, which is x. Carefully took the derivative of square root of y, pulled down the 1/2, subtracted 1/2, and then by chain rule, the derivative of the y value would be 1 dy dx. The derivative of -y is -1 dy dx. A lot of times I like to keep this -1 there just to hold its place so you know there's still a value there. And then on the right side of the equation, the derivative of 5x is 5 dx over dx. Again, if you don't want to put these at all, or if you like that cancellation idea, that's fine. So I went ahead, I grouped everything that has a dy dx on the left side, factored out the dy dx. Anything else I put on the right side. And then I simply divided out by this expression on both sides. Usually we do not like to keep things as complex fractions. The issue was this 2 times square root of y. So I made it multiply by a form of 1. And I distributed it, and this is my answer. Another topic would be, now we're switching integration. So the trapezoidal rule. They're going to try to give you a formula for this that probably seems really complex, or they'll call it Simpson's rule. I would just go with what you know. If they're asking for integration by trapezoidal rule, they're asking you to use an approximation for area of the curve. So I went ahead, I wrote down my trapezoid rule for area here, and I also graphed this from 0 to 8. So this parabola x squared, I graphed the portion I really care about. You will have a calculator. You can always graph whatever that integrand is, and that's fine. And use your table of values if you need to find specific y values, specific function values. So this trapezoid represents all these little trapezoids here. When I talk about the height, that's just the length along the x-axis. So it says you want to approximate using the trapezoidal rule 4 subintervals, or they could say n equals 4. And yeah, so go for it. So 1/2 times the height is 2. Again, they're equal intervals, so you're going to have that throughout. And then I just added the y values. So 0 and 4, 4 and 16, 16 and 36, 36 and 64. As long as you show me this work, you're good to go. Put in your calculator, you get 176. Something that I know will definitely be on the test is average value. There's one of these every single year. All this means is you can integrate and divide by the length of the bounds, basically. For this case, they're saying, hey, I want to approximate the average value of f of x. So we know when I integrate this, I'll circle it, this ends up being basically like my f of x part. And then whatever that is, you can kind of think of it independent. There's my 176. I just look at these bounds. I subtract them. You do the top minus the bottom. So 8 minus 0 gives you 1/8. So 1/8 of 176 is 22. No, not average rate of change. Okay, that's slope, average value. Limits involving infinity. So we're bringing back our first work in this course, actually. So if I'm looking at these, the first 3 are the same. Actually, I made a little typo there. Sorry about that, but I wrote it in. And we're looking at patterns here because they're all going to either negative infinity or infinity. The first pattern, I look at the largest power in both the numerator and denominator, happens to have the larger power on the bottom. So as x gets more negative or even more positive, if it went to positive infinity, that denominator gets larger and larger and larger and larger. So it pulls the overall number down to 0. Whereas with the next one, the powers were equal, so they have equal weight on each other in play. It doesn't matter if the number is getting bigger or smaller. But as it goes to, in this case, positive infinity, the ratio between those, the coefficients, would be -6. And the last one, if you have a situation where it's top heavy, so the larger powers in the numerator, technically the limit does not exist. But usually we try to figure out, does that limit get large and go, or does the value, get large and go to infinity, or get really small and go to negative infinity? So I would still focus on looking at the ratio of the largest powers. Sometimes it's nice to reduce things, so I just reduced x cubed into here, x to the 4, so I got -6x. And then I ask myself, what happens when I plug in a negative number? Well, this becomes a positive number, so that I can say the limit is infinity. The two situations that can be a little tricky with infinity and negative infinity are the classic square root problem. So notice I'm still doing the same thing. I'm still circling the greatest power in each. And I'm going to start at this point. So before I simplify anything, I think to myself, okay, I'm going to infinity. So 6 times a positive, overall will be positive. I make a little note of that. This gets squared first. So remember, you input it, gets squared. It's always, 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 always positive. So I put a positive there. I then reduced. So the square root of 4, x squared is 2x. I reduced the x's. I know they're both positive, hence my notes. So it reduces to 3. If you go the other direction, so you go to negative infinity, again, assess before you simplify. If I plug in a negative value to the 6x, it goes to a negative value. Again, I plug in a negative, but I square it first. This is always positive. So what I chose to do is I said, when I reduced, I just put in my negative. I know that's going to be negative. Put into the equation. You end up going to -3. You will have a calculator. So I still want to see some of this work and analysis, but you can always graph the function, and look at the value as you go to the left and the right. Now the last one is, I stole this term from a packet, a twist on U substitution. So you will most likely look at this and say, I could distribute, I don't know if it's going to get me anywhere, but I know it's a square root. So I think for the most part, you would say, all right, yeah, the U is 2 minus x. Take your derivative, cross multiply, whatever you want to do there to make your du by itself. And then when you plug things in, yeah, you can plug in your u here. So you're good to go. You can plug in for dx, your du. So I have that. I put the negative out front. But this doesn't cancel out. So you don't want to have something with a u and then an x. 2 different variables, that's not helpful. So I would go back to this initial step. So let's get x by itself. So x is the same as 2 minus u. So I did get another substitution. As you can do whatever you want that's algebraically legal. So I took my x, I put in 2 minus u plus 1. If you need to take a step to simplify that as 3 minus u, go for it. I just went ahead and did my next step and I distributed this. So I have 2 and the 1, so that's 3 u to the 1/2 minus u times u to the 1/2. I add the exponents, so you have 3 halves now. Kept the negative out front. Everything is in terms of u. You're golden, good to go, integrate. Integrated, I added 1, multiplied by the reciprocal, so both terms. I even simplified a little bit more because I just wanted that next step, so I didn't make any mistakes. And then I plugged back in my x values. So again, if it's not definite integration, so there's not bounds, even if you do u substitution, end with the x's or whatever the original input was. You can see here I did a little check. Sometimes the checks make sense and you feel confident. Other ones, I think this one's a little bit more challenging and you might feel more inclined to distrust your process.